Is going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Today, we are starting our discussion on capacitors. We just finished our discussion on resistors. Now we're going to talk about a different part of a circuit known as a capacitor, okay? I've got some examples of capacitors right here. They are these little, they have different shapes and sizes. These are very large capacitors, actually. In fact, on there somewhere, one of these even says this is a super capacitor. You can see it right there, 1 farad super capacitor rated at 5.5 volts. These are very large. Capacitors generally are in your in devices. They do. They regulate voltage. They store charge, they regulate voltage. But before we talk about capacitors and go into this unit, let's review the basics of what a capacitor is. And I know what you're thinking to yourself. You're thinking, Mr. Gustin, how can I review the basics of capacitors if we've never learned capacitors? We've learned capacitors. I'll show you. Let's go. We have talked early in our Unit 1 in electrostatics. We discussed what parallel plates were. So 1, 2, 3, 4, 5. I got 5 positive charges over there on this plate. We'll put 1, 2, 3, 4, 5 negative charges on this plate over here. A parallel plate or a capacitor, most capacitors, are just considered parallel plates in a circuit. So let's go back and think about what we did with parallel plates and what we learned about them. The first thing we learned about parallel plates is that charge gets stored on them, right? And when there's charge stored on them, we see a difference in potential. We have a high potential plate and a low potential plate, which means there's the possibility for charges to move. Now, between these plates, as long as there's nothing there, if there's a vacuum between them, no charges will flow. But as soon as you introduce charges in between these plates, well, then they start to move. And based on the charge that they have, they would move either from high to low or from low to high. We show that motion, or we show the predictivity of that motion using a couple different lines. The first line we use is the equipotential line. We said right here down the middle, let's call that a 0 volt equipotential line. It means the potential between the high voltage and low voltage is 0, somewhere in the middle. We could also say that, let's imagine this is plugged into a 200 volt battery. So we would say somewhere between over here, we would call this positive 50 volts, and we would call right at the plate, we call that positive 100 volts. We do the same thing over here. This would be negative 50 volts, and right at the plate right there, negative 100 volts. These are equipotential lines, and they tell us basically as we move from one to the next, how much potential there is for energy, how much potential there is for motion if a charge were present. If there was a charge there, we could predict between two lines how much change in potential energy there would be if there were a charge. Without a charge, we have potential. With the charge and the plate, we have potential energy. Now, the other kind of line that we show, we predict the motion or the force the object or the charge would feel flows from positive to negative. We call these, and they're always perpendicular to the equipotential lines. These are my electric field lines. Electric field lines are predictive lines that predict the vectors of the force. So if there was, again, a positive test charge, let's go ahead and say we put a positive test charge right there. If we had a positive charge there, it would move. We would predict it to move from the positive plate to the negative plate, and that's how we predict the direction, or we write the direction of E-field lines. So charges can move if they're there. But when you have two parallel plates, there are no charges in between there to do the motion. If you think back to our demonstration, we had the tank. We put this whole thing in a tank of water. We had a positive plate, we had a negative plate. We put this whole thing filled with water, and I made you use your hand. And I said, hey guys, stick your hand like this inside that water between some potential difference, and you felt nothing. You put your hand like this in the tank, and you felt nothing because there was no difference in potential between your pinky and your thumb. I'm sorry, pinky, and that's hard to do, pinky and thumb. No difference there. Because there was no difference, there was no potential for motion. Didn't happen. But as soon as you turned your hand perpendicular to that direction, right, or parallel with the E-field plate, now you have a difference in potential between your thumb and your pinky, and the charges in your hand started to move as they were introduced into that potential difference. That caused your hand to go, yikes, and you pulled your hand out because it caused your hand to twitch up. This is the basics of the parallel plate. Now, we had a couple equations. The primary equation that we had that we used was that the change in potential was equal to the size of the E field times the distance or change in distance you move between them. What that basically meant was if I want to find how much potential is changed, what the potential difference is between 2 points, let's say we take this positive charge. We move this positive charge from this location to this location here. If I know I moved, 100 volts, let's say, or negative 100 volts from here to here, I know how far, if I measure with a meter stick how far that is, I could tell you what the E field was. Or if I know what the E field was and I know how far I moved, I can go ahead and then tell you the change in potential. This equation, though, governs the parallel plate. This is our math for parallel plates right here. Now, all that being said, all a capacitor truly is at its core is this plugged in to a circuit. If it is attached to a battery, I'll make sure I draw the battery right. If it's attached to a battery like this is all a capacitor does. A battery runs and it stores charge. A current flows out of the high potential into the low potential. Battery forces charges up onto this plate. And by default, 1, 2, 3, 4, 5, by default, makes the other plate negative. It forces the charges from one side through the battery up to the next, storing charge on this plate. Now you're asking yourself, why would you want to store charge on one plate? What is possible? What can happen if you store charge on that plate? Well, that's fair, right? Like, what would you do with that charge? Well, once the capacitor is charged, it has the ability to do one of two things. It can either send a lot of charge back through your circuit all at once. Think a defibrillator, right? If I need a lot of charge to go jump start my heart. I've got my patches on, I go ahead, I charge up my capacitor, I charge up my AED, and then I hit the button. It releases all that charge all at once. It'll jolt myself. That's one use of a capacitor. The other use of a capacitor would be to store charge so that charge can then be smoothly delivered back to a circuit to something, say, like, I don't know, that your phone. Like, your phone wants a constant, smooth amount of voltage or amount of charge. The capacitor is one way to do that. It stores charge, and then as voltages fluctuate up and down based on heat and resistivity, this thing will continually serve to produce a consistent charge. Okay? This is the basics. When you think about capacitors, all I want you to do is think, how would a parallel plate behave? Because capacitors at their core are parallel plates that store charges. Where do they get those charges from? They get those charges by the battery pushing electrons through the wires, through the resistors, onto them. And at some point, the parallel plate reaches a maximum store. At some point, the plate can't store any more charge. Well, then it's done. We would say that that parallel plate or that capacitor is charged. In order for us to use the capacitor, we have to discharge it. These are the basics. If you got questions, drop in the comments, send me an email, ask me in class. You know the deal. Till next time, see ya.